Manik Reichegger from the Technical University of Munich in Germany, and he will talk about the space debris extraction of the rotational state from multistatic light curves.
Yes, good morning. My name is Manik Reichegger. I work at the Technical University of Munich, and today I would like to introduce you to a planned project of us on space debris. The topic is extraction of the rotational state from multistatic light curves. And as a short warning in advance, this is a planned project and we don't have started yet, but I will give you a short overview what we plan to do, and yeah. Sorry. First of all, we come to the motivation of it. Due to the rapid growth of space debris, the risk of collision in space is increasing. And on one hand with active satellites, and on the other hand with debris. And this exponential increase of debris must be prevented to maintain satellite and space operations. And to avoid these collisions, it is necessary to know the attitude of the debris and to be able to deflect it to another orbit or to bring it back to Earth. To define the attitude in orbit, one approach is to observe the change in brightness of the reflected sunlight to the observer over time. Due to the changing observation geometry during a pass between observer, sun and object, the sunlight reflects to the observer with different intensities. And in addition, the intensity of the backscattered light changes due to the change of orientation. Depending on which side the satellite or the debris part is illuminated by the sun, the object reflects brighter or darker. And this change in brightness allows to extract some rotation parameters of the observations. The usual method for the recording and analysis of space debris, which was also performed at the Technical University in the past, is as follows. First, only objects with known geometry are observed, and only from a single station, and the change in brightness over time is extracted. The next step is a spectral analysis to find the rotational velocity of the object, and here the most dominant frequency is usually used as a rotation period, and this period is then used for the further processing. The third step is to test different input parameters and simulate a large number of light curves. These curves are created with different input parameters such as surface properties, rotation axis, and orientations at the start of the pass. And then the last step is the calculation of the correlations between the observed and the simulated light curve. And the goal is then to find the most reasonable light curve. At the Technical University, we observed some rocket upper stage and as well as larger satellites, such as Envisat. And here, for example, we can see the result of a pass of Envisat in Munich in November 2020. Here we see in orange the recorded light curve, and in blue the best matching simulated light curve. And to get a good match of the observation and the simulation, one has to find the rotation parameters, the surface properties, the attitude at the beginning, and also a 3D model of the satellite. Yes, the figure on the right shows the starting attitude of the satellite at the beginning of the pass according to our analysis. We have extracted, for example, a rotation period of 113 seconds, but of course, due to the symmetry of the satellite, it could also be a multiple of it. And this already leads to the problems. Problematic with this method are the ambiguities. The spectral analysis reveals several dominant rotation periods and rotations around different rotation axes, as well as different starting attitudes lead to similar light curves. And another problem is that very small changes in the input parameters can lead to completely different simulated light curves. And one possible solution would be multistatic observations. They will resolve some of the unobservable parameters, and by a suitable observation geometry, they will eliminate some ambiguities. And one approach to investigate additional information content would be the Fisher information matrix. This is an analytical expression of the null space vectors, which show the undetectable area of the rotation axis. And the matrix gives information about which rotation axis is observable and which lies in the kernel of the matrix and cannot be observed. And by calculating the two null space vectors, the area can be found which contains all axes around which a rotation is not detectable from a single measurement. And the aim is to define these two vectors for a surface or an object, and to find out which rotations around which axis can be measured and which cannot be measured. And the area that cannot be evaluated is defined by the surface normal vector and the vector that is orthogonal to the normal and eigenvector. And the right figure shows the two vectors for a single square surface. The surface normal vector N1 is shown in dark blue, and N2 in orange. And the vector in gray shows the direction to the observer. And if the orientation of the object or the position with respect to the observer is changed, the vector N2 is moving and the non-detectable area changes. And by a well-distributed multistatic mesh of observations, as well as by the change of the observation geometry during the pass, this non-analyzable regions change, and this area can be minimized. We have planned different analyses at the project, and that would be the analysis of the complementarity of multistatic light curves and what additional information they contain. We will analyze the distribution of the ground stations and the influence of it, the shape, the optical parameters and the size of the object, the orbital attitude of the object, the sensitivity of light curves with respect to the initial attitude at pass begin, and the change in geometry between sun object and observer due to orbital motion, and separately from the change in orientation of the object to rotation. At the moment, the following observatories have agreed to record light curves of space debris with us or for us, and would provide us with information and data for our planned database. These are the observatories Graz, our observatory in Munich of the Technical University, Udem, Wetzel, and Zimmerwald. And the light curves will be recorded with CCD or CMOS sensors, and partly by single photon detectors if the stations have them. Another great goal of the project is also the development of a database. In addition to the multistatic light curves, necessary data for the simulation will be stored there. This includes the brightness metrics, the CAD model, software packages we use for the analysis, data containing information about the sensitivity of the measurement instruments, and the measurement conditions while observing. Yes, we need them for a quantification of the quality of the measurements. And the data are then necessary to be able to combine different measurements at a later moment. All additional useful data about the observed object, such as surface properties, to which category the object belongs, which orbit parameters and mass it has, should also be stored there. And then I already come to the end of my presentation. If there is interest and other observatories would like to participate in the observations or provide some measurements for the database, we would be very interested in a possible collaboration. Thank you for your attention.
Thanks, Manik. We have time for questions. Anything from the audience?
Hello. You see, in all the presentation today has been emphasized the need to validate the observation. Have you think about using topics for validate this approach? Because you know there is a paper with Daniel Kucharski, the main author, and a long list of collaboration where the rotational parameter of topics are very well determined. So you have a target that could be used for a real validation of your project.
Mm-hmm. No, we don't have talked about it yet, but it sounds good.
Okay, we have a question from online, from Michael, and you cap on his question as well. Which method do you use to determine the period of the rotation period, and have you considered the phase dispersion minimization method as well?
We used different methods to extract the rotation period. We tested 6 or 7 different spectral analyses, and but we get sometimes different results, and some results are matching with some papers and some not, and we have to evaluate again which spectral analysis we should use.
Okay. Question from the audience? If not, I would have another question for you, sorry. Do you, if I understood correctly, you are simulating the light curve, right? Then I think you are implementing a 6 degree of freedom propagator. Which forces do you consider in your attitude orbit propagation?
At the moment, we only used OREKit to calculate the orbits, but we don't have talked about what we do then in the project, in the planned project, or what are the next steps.
Okay, so the torques you are not yet clear
Not yet.
what. Okay.
No.
And sorry, another question as a follow-up question. Do you model both specular and diffuse reflection, or only is based on the diffuse reflection for the moment?
Sorry?
You use, in your model, do you assume that your reflection to simulate the light curve is only from diffusely backscattered light, or is also taking into account some specular effects?
It's both. It's diffuse and spectral.
Okay. if there aren't any other questions, I will thank our speaker. So this brings us to the end of the space debris session. If you allow me 30 seconds more from the pause for the coffee break, I would like to remind you that ESA is organizing the second edition of the NEO and Space Debris Detection Conference. As Tim mentioned before, laser will be an hot topic, so we will have probably some outcome for the laser observation and orbit determination as well, based on laser products. So I would like to remind you to join us for the conference. It will be an hybrid conference, so you can also join online. And this will happen on the 24th to 26th of January. It's in person, yeah, it's in person, yeah, fully confirmed. Okay, sorry. And then I would like to reconvene here at 11:25. So thanks again.